this is my app. Look at this fucking thing. So, this is the sound analyzer app. The first thing it has is an action. This is the main action. It uses this sound process class I made to read the files and to analyze. It's got one function to actuate a collapse is open. And then the graph function, which tells it which graph to make using the sound process object, which I'm unpickling. I write it to the local cache using a cloud pickle string, and then when the callback is called, it gets a string representation of the sound process data, which it unpickles thusly. What is sound process? Sound process is this thing that it reads sound, a wave file. It can analyze them using FFT, PCA, and clustering, and then it can make plots, pretty plots. Pretty plots. Some CSS shit. Sound analyzer layout. These are just the dash components that define the layout. So, what's it look like? Let's run it. Sound analyzer. Got a 7-second audio clip here. This is FFT window and FFT step size. Alright, FFT has been run. I should add a little indicator there to say it's been run. PCA to reduce the dimension of the FFT matrix, which has 1200 features, 1200 frequencies for the 1200 sample window. And we're going to decompose them with variance maximizing linear projection to 12 components. Okay, that's run. Number of clusters. Now this is music, so in theory 12 should be enough, but let's reduce it to 9, because I don't think I'm using all the notes. And this is just a feature to remove the high variance features from the clustering, because the clustering information should be in the higher component. And the lowest component will probably be like overall loudness, so that's not really a harmonically informative component. So we'll exclude the first two. Do cluster sounds, and then it will make the plot for us. So there's the sound. Traditionally, you look at a spectrogram, which looks like this. There. So this is the sound, and then each color is a cluster representing a note, and then the heat map in the background is the FFT matrix showing frequency components. So you see the harmonic series of each of the notes. This should be enough information to actually say which note it is, but I haven't done that part yet. So yeah, so there's your sounds classified and thrown into 3D space for fun. This is really not a useful chart, but it's pretty cool to have a bunch of points floating around a completely abstract space. Alright. Fuck. Can't get to the bottom. Somewhere. Okay, that's a little better. Change defaults. A felicidade. 7 seconds. Tristeza não tem fim, felicidade sim. There we go. Alright, so you can increase the dimension up to 12, I guess. Oops, 12. Here's why dimension 1 is not a great clustering dimension. Look at that. Dimension 1 is... which one is dimension 1? This is dimensions 1 and 3. This is dimensions 1 and 2. Boom. Let's do scatter matrix. That'll show all of them. Reduce principal components to 8. Reduce clusters to 9. So there's all our sound data in all the dimensions. Dimensions 1, 1, 1, 2, 1, 3. Yeah, it's just every pair of dimensions. But PC1 has a lot of variation, as it should, because this is principal components, so PC1 has the highest variance, which means it stretches it out a lot in this dimension. So if you include that in the clustering, that dimension will be too important in the clustering. So what I've done is excluded 1 and 2. So just anything from here down you can use for clustering. The PC scores are amounts of frequency component, and each PC represents a spectrum. It's a decomposition of the spectrum. So each one should be like a note or a chord, and I can break the sound down into these segments and see what it sounds like, and then see what the principal component representation of it sounds like, and then see what each component of the principal component representation sounds like. Because the principal components reconstruct one of these columns of the heat map. The heat map is 1200 rows by 7 seconds times 22,000 divided by 30. Whatever that is. So each column is a spectrum representing the harmonic content of the window of 1200 samples. So the principal component representation is trying to recreate those spectra. And so the components that it would use are going to be other spectra that are statistically independent, I guess, is what's going to happen, because there is that orthogonality that has to be present between all of the principal component vectors, or singular vectors, if you like. Three, 4, 5, 6. Okay. Let's try a different sound. Oye, como va? Interesting. Interesting. Now this is making me want to try kernel PCA, because I could probably get the separation that I need in fewer dimensions. Although in theory it should be. You need at least one dimension for every note and chord in the song.